There's the gases in the last chapter, right at the beginning. What solutions are, these are homogeneous mixtures. And so air is a solution. It's a gaseous solution of nitrogen and oxygen. But what this chapter is going to focus on are liquid solutions, not gaseous or solid. Solid solutions are called alloys. And so we have liquid, solid, and gaseous solutions. Chapter 16, looking at liquid solutions. And so there's going to be some terminology, etc. So these are the learning objectives you can go through and take a look. So here we are. Solutions are homogeneous mixtures. Homogeneous just means everything's uniformly distributed. Gas, liquids, and solid solutions. In a solution, the dispersed particles are very small in the liquid solution, so they don't settle. This is two solutions made up of the same substance may have different compositions. Yeah, air has different compositions. Sugar water has different compositions. Depends on how much sugar you have in water. So this slide we can kind of skip over. Solute and solvent. When we have a mixture, there's usually a major component and a minor component. And so sometimes we'll just say, it's dissolved in the major component. So if we're looking at water solutions, the solvent would be water, the solute would be whatever is dissolved in the water. So solute is the minor component, the solvent is the major component. Solutes can be solids, liquids, or gases. Solid would be like sodium chloride dissolved in water. A liquid would be like methanol or ethanol dissolved in water. And a gas would be like oxygen gas dissolved in water. So the solutes can be different bases. Here's the slide just showing. Here we have the solvent, which is water. The solute is a solid solute. This is copper. This looks like copper 2 sulfate. It's not, I'm sorry, it's copper 2 chloride. I can tell based on the anions, it's spherical. These are copper 2s here. Copper 2 chloride is blue. So they take some of this and dissolve it in the water. They can take all of it, looks like, this blue solution. The blue solution, what happens in water is the crystals get torn apart by the water. And so here we see copper 2 ions. These are going to be surrounded by the water molecules. We have the chloride ions surrounded by the water molecules. This helps stabilize the species in the water. And so those are aqueous copper 2 and aqueous chloride ions. This would be considered a strong electrolyte. Strong electrolytes break apart when dissolved. Copper 2 chloride is soluble. If we dissolve a lot of the copper 2 chloride, we'll call it concentrated. If we dissolve a little bit, it's called dilute. It's all relative. How much can you dissolve? Is there any limit to how much you can dissolve? There's a limit, it's called solubility. There's a solubility limit. We can figure out how much we can dissolve. You can't just keep scooping in copper 2 chloride to that beaker of water. Eventually, you're going to hit that limit. Let's see what that limit is. And so we look that up in the handbook or Wikipedia. Let's look it up on Wikipedia. Oops. So if you go to Wikipedia, and we'll just put in a lot of this physical data is in here, Cu, Cl2. We call that limit the solubility. It's given here. The solubility refers to, you can't dissolve an infinite amount of copper 2 chloride in water. Eventually you're going to hit that limit. That limit depends on the temperature. At 0 degrees C, the maximum amount of copper 2 chloride we can dissolve is 70.6 grams. so if we're close to this max, we call it concentrated. If we're far from that max, we call it dilute. What if we're right at the max? If we're right at the max, we call it saturated. It's been totally saturated, it can't take anymore. If it's below the max, we call it unsaturated. The saturation is going to depend on the temperature. So at 25 degrees C, it's 75.7. At 100 degrees C, it's 107.9. That's all. You can see the solubility increases with temperature. It makes sense. Why does that make sense, that the solubility would increase with temperature? Yeah, you could. It's easier to break apart the crystals, with more kinetic energy. Break apart. This is solubility. We don't have to use water as our solvent. They're what we call non-aqueous solutions. So for example, we might try a different solvent like methanol. If we tried to dissolve our copper 2 chloride in methanol, how much can we dissolve? And it looks like it's a little less, right? 68 grams here in methanol at 15 degrees. Ethanol, 53 grams in ethanol. So we could try different solvents. Some things turn out to be more soluble as non-aqueous solvents. Non-aqueous means not water. Some things turn out to be less soluble than non-aqueous. There are things that are infinitely soluble in water. Infinitely soluble would be something like water in water. How much water can you dissolve in water? Infinite. Right? Infinite. But methanol is very similar to water. Methanol loves the hydrogen bond. Water loves the hydrogen bond. So methanol and water are so similar that they're infinitely soluble in one another. You know what we call it when something is infinitely soluble? We call it miscible. So methanol and water is miscible, M-I-S-C-I-B-L-E, miscible. We're going to see that later. But some things hate water, like oil. Oil's immiscible in water. Methanol is miscible in water. Well, anyway, let's take a look at this concentrated versus dilute. You can tell by the color here. This is dilute, that's more concentrated. This is a reaction. This is copper wire and silver nitrate. So you can see this coating is silver metal. It's a single replacement reaction. The coating grows. Do you see these? These are called dendritic crystals. They look like little trees with needles. Do you see those?
Yeah.
These are crystals of silver. Silver forms dendritic crystals, big crystals of silver. Well, what's happening? The silver nitrate's attacking the copper metal, making copper 2 nitrate. And so on the left we see dilute copper 2 nitrate, on the right we see concentrated copper 2 nitrate. The solubility, again, is the maximum amount. If we want to know what the max is, we look at the solubility. It's going to be a fixed number. Or it might be miscible, or it might be immiscible. A saturated solution is a solution right at the solubility limit. We can't dissolve anymore. An unsaturated is below the solubility limit. We have miscible. Miscible means what? It's infinitely soluble. The soluble, this is tricky. It's infinitely soluble. Immiscible means, yeah, it's not soluble at all. Infinitely versus zero. Well, zero is very tricky because even if it's zero, so in methanol, it's 68. In ethanol, it's 53. What is it in acetone? What is the solubility in acetone? looks like it's it looks like it's miscible in acetone. It looks like it's infinitely soluble. It looks like, eventually you're going to have a solid solution. What about this word here, supersaturated? Supersaturated takes advantage of something. For something to precipitate or crystallize, crystals have to form. But sometimes crystals are hard to form because everything has to line up perfectly. If things don't line up perfectly, then crystals don't form, crystals don't grow. Now, it depends on how difficult it is to line things up. Like, say you have an acetate ion. If you have an acetate ion, you look at the structure of acetate ion. The structure of acetate ion looks like this. Negative formal charge there. Has this, it's tetrahedral here. What is it here? Trigonoplanar. Now this ion has to line up perfectly, right, in order to form a crystal. In order to form a crystal, something like sodium acetate. Well, how, this is kind of big ion, and you got to get it perfectly aligned in the crystal. It means that crystallization is sluggish, because what is the probability of getting it perfectly lined up? The probability is kind of low. Versus other ions, compared to chloride ion. What is the probability of getting a chloride ion perfectly lined up? It's very easy, because chloride is just a ball. It's always going to be lined up perfectly. And so chlorides are easy to crystallize. Acetates are hard to crystallize because everything has to line up. So let's take a look at supersaturated in action. What happens is, if crystallization is sluggish, like sodium acetate, we'll just do that. We'll just take the first one. So what happens is you get it hot. And when it's hot, can you dissolve a little bit or a lot? A lot. And so it's hot. And then you cool it down. When you cool it down, then what happens to solubility? Solubility goes down. Not as much dissolves. But that means any excess, so if we took this hot sodium acetate solution and cooled it down to room temperature, that means any excess should precipitate out. But what happens is those acetates are hard to line up. And so what we end up with is this. This is room temperature sodium acetate with way too much dissolved, much higher than the solubility limit. And so this is what we call supersaturated sodium acetate. Supersaturated sodium acetate, well, we need something to help it. What's going to help it is putting a seed crystal in there. What a seed crystal does is it provides a little crystal here where the acetates are already lined up and the sodiums are lined up. And so it's much easier to, if you have a seed crystal in there, to add more acetates and more sodiums to that crystal to make it grow than to do something called nucleate. To nucleate a new crystal from nothing, we got to have the sodium and the acetate come together and cluster all at once. And so the seed crystal provides a template in which to line up all the other ions. So in this case, I think they're just going to drop a seed crystal in here. Take a look. Oops. you see that? There's way too much solid dissolved in there, so all that crystallized out of there. Other ways you could do it, there. Do you see that they're dropping the seed crystal in? Or, there we go. Seed crystals on a stick. Sometimes scratches will help. Sometimes other ways will help to get the crystals nucleated and start growing. So it forms very nice needle-like crystals. That's what happens with the supersaturated. Let's take a look at one other one. This just goes to show you the extent that it's supersaturated. We put a seed crystal on the watch glass, so the crystals can grow here. You can see as the crystals come.
Tower of sodium acetate coming out of the supersaturated solution.
What was that noise?
It's gonna fall over. It's gonna fall over. Great job.
I'm done. No, I want to stand.
Are you
on this
sick?
phone. Yeah.
You too, no?
We have to match the rest of our calendar in. Or leave it there. You just leave it.
Alright, so here's.
Raymond, I think you're gonna win the award for the tallest sodium acetate tower.
Class 4, is it hot?
Let's not touch it.
I don't want it to flip. It's going to flip.
You know what they're gonna ask you? Is this an example of a stalagmite?
Alright. So here you can see they drop there's a seed crystal, drop it in there. But that happens just for things that are hard to nucleate. All right, let's talk about miscible and immiscible here. Yeah. And again, it doesn't have to be water as a solvent. So for example here, the solvent is octane. It's hard to tell which one is the solvent. The solvent's the one in larger quantity. It looks like maybe octane, but in this case it really doesn't matter because these two liquids are miscible in each other. And so octane and carbon tetrachloride are miscible. You can mix them in any proportion you want. However, gasoline, which consists of a lot of octane here, is not miscible in water. In fact, they stay separate here. So two immiscible liquids here. Same thing with carbon tetrachloride. Carbon tetrachloride would sink to the bottom here because it's more dense. Here it's permanently suspended because they like one another. The reason why is it has to do with intermolecular forces. You know, octane's nonpolar, carbon tetrachloride's nonpolar. And so when we have nonpolar molecules, we're looking at instantaneous induced dipole. Give me another name for instantaneous induced dipole. Give me two more names for instantaneous induced dipole. Well, one name is going to be called dispersion forces. The other name is called London forces, or London dispersion forces. And so London dispersion forces, you know, both of these love London dispersion forces, so they both love each other in that case. Whereas water likes hydrogen bonding, gasoline likes dispersion forces, so those forces don't match. And so then we have a rule. It's called the solubility rule for molecular compounds. Do you guys remember the solubility rules for ionic compounds? Yeah. Long list. Well, these ones are easy to memorize. The solubility rule for molecular compounds is like dissolves like. So carbon tetrachloride, octane are like in that they both like dispersion or London dispersions. But unlike, don't like each other. So this is dispersion, this is hydrogen bonding. Methanol likes water because they both like hydrogen bonding. Like dissolves like. To put it in the simplest terms, it goes like this. Polar dissolves polar. Nonpolar dissolves nonpolar. But nonpolar and polar don't mix. And so polar likes polar. We talk about polar, right? Polar is positive, negative. Okay, let's talk about formation, solution formation next. And we're going to look at it here in this slide. So sodium chloride is very polar. Ionic bonds are the most polar you can get. So sodium chloride is very polar, water is very polar. So they like each other. And so what happens here is, here we have a crystal of sodium chloride. The water molecules are attracted to both the negative ions and the positive ions. And then if there's a collision strong enough, the ions can get knocked off the crystal. And so there are lots of collisions in here. Some of the collisions are weak, some of the collisions are strong. You have a distribution of energy. But eventually what happens is that that crystal gets torn apart and makes these ions. These are ions dissolved in water. Now, the positive ions are going to be surrounded by the oxygen end of water. The negative ions are going to be surrounded by the hydrogen end of water. When an ion is surrounded or encapsulated in water, we call it a hydrated ion. And so this is a hydrated chloride ion, this is a hydrated sodium ion. These hydrated ions are stable because of the electrical interaction with the ion and the water molecules. So, let's take a look at this. So, polar, and we talked about polar molecules earlier. Here they're looking at the dissolving. This is actually a physical process, not a chemical reaction. They're dissolving ionic crystal, sodium chloride, in water. There are ions on the surface. Those are going to attract the water molecules. There are collisions. Those ions break off to form hydrated ions. We will represent this whole process like this. Take solid sodium chloride and dissolve it. When we dissolve, the ions break off, or break apart. We're left with the hydrated. So Na plus AQ is the hydrated sodium ion. Cl minus AQ is the hydrated chloride ion. This is called a dynamic equilibrium because what happens is, can you dissolve an infinite amount of sodium chloride in water? Is sodium chloride miscible? No. It's about 36 grams. And so if I had more than 36 grams, I'm going to have a dynamic equilibrium. If I have, let's say, 37 grams, then what's going to happen is, the forward process, which is called dissolution or dissolving, is equal to the reverse process, which is called crystallization or precipitation. And so if I put in 37 grams, the extra 1 gram just doesn't sit there. The extra 1 gram is continually being cycled like this. And so if you have a supersaturated solution, if you have a saturated solution and add more solid to it, you'll notice the crystals start to change. Because crystals are always dissolving and crystals are always forming. So the crystals are always changing. The mounts don't. That's the dynamic equilibrium part of this. So if we put in way too much sodium chloride in here, then the dissolving or dissolution never stops. And crystallization, sometimes this sodium will strike the surface and stick. it strikes the surface and sticks, then it breaks out of this hydration sphere, crystallizes. The same thing with the chloride. It could strike and stick. But eventually, if we have too much solid in here, the dissolution that is dissolving is equal to the precipitation, that is the crystallization. And if those two rates are equal, then there's no more change. No more. That's 36 grams. But there's always change. That is, if I add more crystals in there, those crystals just don't stay there static. The crystals are always dissolving and always crystallizing, but there's no net change because it's just going in circles. You will see a change, though, in the crystals themselves because you'll see new crystals form. Old crystals being replaced. So this is a process. Here's unsaturated. In an unsaturated solution, so let's put some crystals in pure water. And the only thing that's going to happen is dissolving or dissolution. But as the concentration of ions increases in water, then those ions can strike the surface and stick. That's crystallization or precipitation. Initially, there aren't that many ions in water, and so the rate of crystallization is smaller than the rate of dissolution. But eventually we get so many ions, and it becomes concentrated enough that the ions sticking are sticking at the same rate as the ions that are dissolving. In other words, the dissolution rate is equal to the crystallization rate. You have a situation where there's no more net change. However, it's going in circles. It never stops. So this is dynamic, but since it's going in circles, there's no change. It's in equilibrium. It's in dynamic equilibrium. So let's take a look at things that affect solubility. One thing that affects solubility are the forces. You know, like dissolves like. Another thing that affects solubility is temperature. Now, temperature, we have to look. You know, higher temperatures, are things more soluble or less soluble? More soluble. But that only holds for solids and liquids. Solids and liquids tend to be more soluble at higher temperature, but what about gases? Gases become less soluble at higher temperatures. So if you have a lake, you know, and you have oxygen dissolved in the lake for the fishes, if the temperature of the lake increases, is there more oxygen or less oxygen? Less oxygen. So solubility of gases decreases with increasing temperature. But there's also something called pressure that affects it too. So let's look at these factors individually. So like dissolves like. Oil, this is water. Water and ethylene glycol antifreeze. Ethylene glycol has two carbons like this, so CH2, CH2, and then it has an alcohol. It has two alcohols. If it has two alcohols, this is more water-like or more oil-like? This is more water-like. So this is water-like, this is water, like dissolves like. Ethylene glycol is miscible in water, antifreeze, miscible in water. How about oil in water? Oil, non-polar, water polar, immiscible. Ethylene glycol, very polar, water, very polar, miscible. In fact, so polar they hydrogen bond. Hydrogen bonding is the most polar you can get with polar covalent bonds before going ionic. Okay, gases. You know, some gases are really soluble in water. Can you name two gases that are really soluble in water? Not CO2. CO2 isn't very soluble in water because CO2 is non-polar, water is polar. So if you exhale, have you exhaled underwater, what happens? Bubbles float to the surface.
What about oxygen?
Oxygen's not very soluble. Oxygen is non-polar, water is polar. It doesn't mean, you know, a little bit of CO2 dissolves in water. Have you seen a little bit of CO2 dissolve in water?
Yeah, so
Yeah, it makes carbonic acid. A little bit of O2 dissolves in water, otherwise marine life couldn't exist. But it's not a lot. Yeah, those are soluble, except think of a gas, because most carbonates and nitrates are solids. Now think of a gas that's pretty polar. Ammonia. Ammonia is very soluble in water. Ammonia. You could dissolve lots and lots of ammonia in water. You can't dissolve lots and lots of CO2 in water. So ammonia is one of the ones that are very soluble in water, and not nitrous. It would be, makes an acid though. Hydrogen chloride to make hydrochloric acid. Hydrogen chloride is very soluble. Both of those, ammonia and hydrogen chloride, are very polar, and therefore very soluble. Well, if I have something that's not very soluble, how can I increase its solubility, like CO2? If this is CO2, a little bit can be forced into the water, right? Because this is what we call the partial pressure. There's going to be collisions, and those collisions cause them to stick in the water, forced into the water. If I increase the pressure, then you're going to get more collisions, more energy, or actually not more energy, it's the same energy. You're just going to get more collisions, which means more soluble. And so this is like soda water. If you buy a bottle of soda water, what is the CO2 pressure? Do you know what the CO2 pressure is in they call it the head space of the bottle? There's some gas in there. And so let's say you bought some sparkling water. So what we're doing is we're dissolving the CO2 in the water, the sparkling water. And that means there's CO2 here. If there's no CO2 here, then it can't sustain this. The CO2 will escape. So there's CO2 being forced into the water and CO2 escaping. That's called the dynamic equilibrium. Is this high pressure gas in the bottle, sparkling water? If you shake it, it is. If you shake it, agitating makes this less soluble. But what if you don't shake it? Is it under high pressure in here? No. You know what the pressure of the gas in here is? Atmospheric pressure. 1 atmosphere. Well, what happens is this. It's 1 atmosphere of pure CO2. It's not 1 atmosphere of air, it's 1 atmosphere of just CO2. What happens if you open the bottle? If you open the bottle, then air gets in. And how much CO2 is in air? Very little. What is the partial pressure of CO2 in air? So we're going to go from 1 atmosphere to, let's see if I have this. We're going to go from 1 atmosphere to 0.0039 atmospheres. So if we open this bottle of CO2,
So the pressure is going to decrease.
yeah, the pressure is going to decrease. And so if we open the bottle, all of a sudden we got lots of CO2 here dissolved here. But up here we go from 1 atmosphere to 0.00039 atmospheres because it's a percentage, so I'm just going to convert it into decimal. So what that means is this is going to be super saturated. Because CO2 bubbles are hard to nucleate. They got to grow. Let's see if you got to line them up. And so there are things to help nucleate those. One thing is shake it up. That'll help nucleate. Then it'll go from being super saturated to flat. Another thing is you can put a seed crystal in. But how can we put a seed crystal of CO2? We don't put a seed crystal of CO2. You don't have to put in CO2. You can put other species in there that could help act as a seed. Well, what are some of the other species you can put in there to act as a seed? Mentos. Mentos, I guess. Mentos candy can act as a seed. You've seen this, right? Let's just pick the first one, hopefully. This is a demo you could do at home. And this is long. What happened there? Oh, there's too many ads. Nucleation of bubbles. About 50 feet per second. All right, so here's a little graph showing. So getting back to this, there's a huge imbalance now. There's way too much CO2 that CO2's got to escape. But since CO2 bubble formation is difficult, since CO2 bubble nucleation is difficult, it's sluggish. So if you can speed it up, you can really get it to go. All right, let's take a look at temperature next. And when we look at temperature, if we increase the temperature, what typically happens in solubility? As we increase the temperature, the solubility goes up for solids. These are all solids. However, some solids, the temperature actually goes, results in a decrease in solubility. This is unusual. Most things increase in solubility. Gases decrease in solubility. Another way to get this is heat it up. And so ammonium chloride here. Ammonium chloride at high temperatures is much more soluble than at cold temperatures. So ammonium chloride is dissolved in warm water. If we cool it, what's going to happen? Well, when we cool it, ammonium chloride is going to precipitate out. Now, is ammonium chloride sluggish? No. So ammonium chloride is easy to nucleate because ammoniums are tetrahedral. Tetrahedral is spherical in shape. Chlorides are spherical. And so making crystals of ammonium chloride is easy. If this were ammonium acetate, a different story because ammonium, spherical, acetate is that shape. Ammonium acetate would have probably had a hard time precipitating out of here. anything with odd shaped ions can result in supersaturation, or anything that are sluggish. All right, now once we form a solution, this you just need to know typically increases for solids. This decreases. Once we know, once we have a solution, then we want to characterize the composition of the solution. The composition, in other words, is called concentration. Composition or concentration of the solution is going to be given by different units. One of the units that are common is percent by mass. Percent by mass is just the mass of solute over the mass of solution times 100%. The mass of solution is the mass of solute plus the solvent. In other words, the total mass. And so it depends on how many solutes you have. Mass of solute A over the total mass times 100%. Mass of solute B over the total mass times 100%. And so percent by mass, we can figure it out. Let's take a look at the example calculation here. 125 grams of the solution was evaporated to dryness. 42.3 grams of solute was recovered. And so the total mass is 125 grams. That's solution. Solution consists of solvent plus solute, so 125 grams. 42.3 grams of solute was recovered. So if it's 42.3 grams of solute, then that means the rest was solvent. So we can calculate how many grams of solvent we have, but we don't need that because the percent by mass of solute is 42.3 grams divided by 125 grams of total times 100%. Let's take a look at this. Calc here. So it's the mass of component A divided by the total mass times 100%, which is 33.8%. They don't use the unit here, percent. I use the unit percent. It's important because if we multiply this by 100, we get percent. If we multiply this by 1,000,000, do you know what we get? Parts per million. If we multiply it by 1 billion, we get parts per billion. So 33.8% would be 33 what would it be? A million. This is 10 squared, 10 to the 4th. So 1, 2, 4. It'd be anyway, it'd be a big number. That's, we use parts per million if we have a tiny bit. Let's say it wasn't 42.3 grams. Let's say it was 42.3 micrograms per 125 grams. That's extremely, extremely small. And there, if we multiply by 100, we're going to get a tiny number. So let's multiply by 1,000,000 or billion, get a better number to deal with than that. And so I'd like to have the units there because 100 is for percent, 1,000,000 is for ppm, and 1,000,000,000 is for ppb. Okay, what we'll do is we'll stop here to the end, and then we'll continue. This next calculation will take a little bit of time. So let's just stop.